Hi, hello everyone. Welcome to another episode of the Koi podcast. So, as you know, that in this podcast series, we have been talking with various, mostly early career researchers who are doing a lot of state-of-the-art research in various topics across the earth science and even tangential. We have also talked about a bit of different topics. So today we're going into sort of again into the polar world. So as you know that I have a personal interest in polar sciences in general, but today we are going to talk about freshwater studies in polar marine systems. So when we think about the polar system, we're mostly thinking about ice, but it's a matter of fact that freshwater rivers and freshwater systems um, are vital in even the polar marine systems. So that is what we are going to talk about today. And to talk on this topic, we have with us Atreya Basu, who is a PhD candidate at the Center for Earth Observation Science at the University of Manitoba. Atreya was a personal sort of mentor for me when I was doing my master's also at CEOS, University of Manitoba. So it's a pleasure for me to have him on this podcast. So thank you so much, Dada, for doing this. Yeah. And
And thank you,
yeah, if we
Monaji.
just start off, so basically we can start off. If you just want to sort of briefly introduce yourself and what particular research you're doing now. Yeah.
And first of all, thank you, Monaji, for inviting me to Koi. I think this will be my very first podcast that I will be in through my research career. So thank you for giving me this platform. I'd like to acknowledge you for this. So I am basically a remote sensing scientist. So and which where I'm studying the freshwater in the polar marine system. So basically, I have a very deep interest in marine science. Now, how I developed it, it was like I still remember in my young days, I used to stroll around in the beaches and used to see the sands moving around, coming with the waves, getting back the waves. And there was a change in the color of the seawater as we see move from the coast to offshore region. So this is what particularly motivated me to study marine science, this change in the color.
Mm.
So that's where I started doing my master's in marine science at University of Calcutta, India, which is in Kolkata. And then from there, I got to learn that if I want to see the colors, my eyes can see till a limited distance. I cannot see the wide area.
Right.
Even if I'm on the field or in the boats or in the ship, I can't see it.
Mhm.
So I
Right.
decided, what is the thing that will make me able to see the whole system? So satellites was the answer for it. Satellites
Hmm.
can see the wide space area. So I did my second master's in remote sensing and GIS in marine and atmospheric science from Indian Institute of Remote Sensing, which is a part of Indian Space Research Organization. And from there, uh, garnering all the knowledge of remote sensing, data processing. I got this opportunity to work in this beautiful place in Canada, in CEOS, where I got deeply involved in studying polar marine system and how freshwater is getting distributed in this whole polar system.
Hmm.
So, and by the time when we are talking about freshwater, the first thing that comes into our mind is sea ice,
Hmm.
which is a solid form of the fresh water.
Right.
But there is also a liquid form of the fresh water,
Yeah.
which is rivers,
Hmm.
the rainfall, or the snow or the precipitation. And then, so this together, the system, how a freshwater behaves or it's distributed and dispersed within a marine system is a main topic of interest during my whole PhD. And my
Okay.
study area is Hudson Bay and the James Bay.
Right. Okay. Thank you so much, Dada. That was a very, I really enjoyed how you linked your current research interest in marine science to particular observations. So I think we scientists, like, well, aspiring scientists, we always have those one moment where you really try to understand that, okay, nature is worth sort of investigating. So thank you for sharing that info. As you were saying, that your topic is in the Hudson Bay and the James Bay, James Bay system. So, if you just want to sort of first tell us a bit more about sort of the setting, or maybe just for a general audience, what this system attains to, and then if you can give us a brief intro about your PhD focus, like what part of this system you're focusing on.
Yeah. Monojit, Hudson James Bay, these two systems are very inland seas. Like it's a very enclosed sea. It's all land all around, and there is a very narrow opening which connects either to the Arctic Ocean and one to the North Atlantic Ocean. And the main thing about Hudson and James Bay, it's a very shallow system. So roughly it is around 150, and on average we can say it's a 150-meter deep. Whereas if you go to the world oceans like in Bay of Bengal, it's quite kilometers deep.
Yeah.
So it's just 150.
Okay.
So it's a very shallow system. But the interesting part is, in this shallow system, there are about, like if we count, it is around 42 rivers that drains into the this shallow system. Now,
Right.
if we look into the rivers that comes around the whole Arctic Ocean and rivers that comes into the Hudson Bay, so what we do is call a runoff yield, which is like the river runoff, that is a discharge divided by the surface area. So if we do compare this runoff yield of Arctic Ocean and Hudson Bay is 3 times more runoff yield than the Arctic Ocean. So
Okay.
it has more. I'm not saying that it has the volume of the river runoff is more than the Arctic Ocean. It's not that.
Yeah.
Arctic Ocean is always has a huge volume of rivers coming in.
Yeah.
But compared to the area, when we normalize it with the area, we see that there is huge volumes of like the river layer water is forming over there. And so thereby this shallow system with this high runoff yield forms a very unique freshwater system where river water is a very important part of the whole process. Now, the most important thing of studying freshwater is that if we go even in the polar system, if there is more freshwater in the system, we get stratified. Now, stratification in very simple terms, what we see, it's a layering of the seawater. Like if we have a glass of water and then we pour some oil over it, we can clearly see the oil and the layer of the water separated. It's the same thing like that. It's the same thing like that. So if we have more river water on the top, we're going to have the more river water in the top and the dense seawater in the bottom.
Right.
So, excuse me. So if we have more river water in the system, the thing is that the heat that enters from the Atlantic water into the Arctic Ocean from below is not be able to go into the top layer.
Right.
So if it doesn't go into the top layer, it will be unable to melt, or rather what I will say is like it will be like preventing melting of the sea ice. It should prevent more formation of the sea ice. On another hand, if we look, it is like if we have more like a layer of fresh water on the top surface, there will be no mixing because there will be no mixing in the water column. And if there is no mixing in the water column, the nutrients from the below the ocean will not be coming into the top of the water, top layer, and thereby the primary production will be theoretically halted. It is not, but theoretically it will be halted. So it's very important to study how much of this fresh water is coming into the system. And several studies have already stated that this fresh water from the Arctic might impede or slow down the Atlantic meridional circulation by disrupting the Labrador, like the dense water formation which is in the North Atlantic Ocean. So it might impact the
Okay.
global climate. So fresh
Hmm.
water in the polar system is very important. And
Important.
here, like there are many studies that happens in the whole Arctic Ocean wide. But what I
Hmm.
felt during my PhD, Hudson Bay is the most neglected part, being such an important contributor of river water, as well as sea ice also.
Hmm.
So
Right.
this is what prompted me to see that how much of this fresh water is coming into the system, how it is getting dispersed over time, and see where it is going into the open ocean, like in the
Right.
North Atlantic or into the Arctic Ocean in this
Hmm.
strait. So this is what motivated me to study freshwater dispersion in Hudson Bay.
Okay. Yeah, that's very clear. Just chiming with the with what you said about studying of the Hudson Bay. I totally agree because whenever we see Arctic studies, there is a lot of focus in the Central Arctic. So the Central Arctic ice pack and the geoprocessing, even the large expeditions such as Mosaic, they're all focused towards the Central
Yeah,
Arctic.
yeah,
But having
yes,
said
yes.
that, regions such as Hudson Bay, which are going to play increasingly important role in the coming days with the changing state of the sea ice, these are often like not studied well enough, and that's where I think your PhD focus is very vital because that gives us a very unique information about these systems and how the dynamic works in general. So yeah. Research Letters, which is one of the most well-renowned journals in our field, as we know. So basically, recently in January, the paper titled "Satellite Data Trace Seasonal Freshwater Dispersion in Hudson and James Bay." So this paper, published in GRL, as we are talking about, was authored by Atreya, and so we would like to know a bit more about this publication. What is this particular publication? Why it is important, or what was the process behind going through this publication?
Uh, Monojit, this publication is my second publication for the PhD.
Right.
And
Sorry.
this publication is mainly to distinguish between the two important freshwater components in the in any polar marine system, we can call it, not specifically to Hudson Bay, which is river water and sea ice melt.
Hmm.
The problem is, traditionally in the field, we can do this using various methods, like mostly using salinity data, temperature data, and we can use oxygen isotope data, which can differentiate between sea ice melt and river water. Right. But the question was, if we want to detect it from the satellite, what was the best way of distinguishing between river water and sea ice melt? The problem was of this paper was satellite detects salinity. But from using salinity, I can quantify the total freshwater.
Hmm.
So I know my reference freshwater, like the reference and member value. Okay, I can see that, like for Hudson Bay, you can see like 32.5. If we reach a salinity of 32.5, we can say that's a marine water. So any other like 23.5, we can usually calculate that how much of freshwater is there in the system. But how can we see that there is a freshwater from rivers or freshwater from the sea ice melt?
Hmm.
We can't do
Okay.
that.
Yeah. Yeah.
So here, what I introduced is another tracer, which is called colored dissolved organic matter, which is CDOM, CDOM in normal
Mhm.
words we call it. And so this CDOM is nothing but, how will we explain it? Very simply, if we have uh, a like the tea leaves, if we consider tea leaves and a glass of water. So
Mhm.
consider the water as the river and the tea leaves as the leaves of the real, like the terrigenous things. And if it falls into the, like in the teas, it gives color to the
Right.
water.
Right.
Yeah, colored dissolved organic matter. It's a dissolved organic matter from all the terrestrial, like leaves falling into the system, the soil coming into the river water. So it gives a coloration to the river water. So it's same thing if we consider that it's a tea leaves giving color to the water.
Water.
Just if
Yeah.
we draw an analogy to it. So
Right.
now if we trace, yeah. So if we trace that color from the rivers into the estuary and then into the open ocean, we can trace the river water.
Mm-hmm.
So the color, tracing the color of the river water or of the water in the ocean, we can differentiate between river water, which is very CDOM rich,
Mm-hmm.
and sea ice melt, which has no color at all.
Right. Right.
So using this technique of using CDOM rich river water and CDOM free sea ice melt, along with salinity from the ESMOS satellite of European space agencies, we can differentiate between river water and sea ice melt from space.
Okay.
So this was the basic concept of the paper. Now, using this analysis, what we observed is that normally we found that the river water was increasing in the fall time. But
Okay.
normally, what happens is during the fall, the river discharge is low.
Right.
At least compared to
Right.
June, when we have the major amount of freshet, there
Yeah.
we can expect there is high amount of river water. The CDOM will be high, so we can trade. But we were surprised to see that in fall season, when the river discharge was low, we are seeing there is an increasing amount of CDOM in the, or rather river water in the system. This astonished us, and this is what paper highlighted in the system. Now we went further into discussing that what is causing this kind of anomaly in the system, that how it's happening. So we realized that it's a winds that plays a role. Not only river discharge is the most important part of
Mm.
distributing fresh water in the whole Hudson Bay system. It's the winds that redistribute this river water into the system. Like if we have, it's in a very simple things. If we have an anticyclonic circulation in the system, like if there is an
Mm-hmm.
anticyclonic winds blowing in the system, we'll have an anticyclonic circulation, which will allow fresh, like waters from the coast to travel into the offshore water.
Okay. Right.
So water from the coast goes into the central Hudson Bay.
Right.
And if there is an opposing wind direction, which is the cyclonic formation, cyclonic winds, water from the offshore
We'll come to the. Okay.
comes moves towards the land.
Okay. Okay.
When
Okay.
it moves, when it pushes this water towards the coast, there is a downwelling of water. Like the water moves down. There's a downwelling
Mm-hmm.
of water. So the river water moves down into the water column.
Okay.
So it's not only the river discharge, but it's the water that is penetrating down that is causing the entire river water to increase in the whole system along the coast in
Okay.
Hudson Bay
Okay.
during the fall, which is cyclonic duration or the cyclonic circulation timing over there. So this
Mm-hmm.
was pretty
Okay.
interesting for us to see that this kind of phenomena is taking place in Hudson Bay. And to note, this kind of phenomena also takes place in the Arctic Ocean also. The
Okay.
phenomena, we call it the Beaufort High and the Beaufort Low.
Okay.
The same phenomena just takes place in the Arctic. We were surprised to see it.
Mm-hmm.
So
Mm-hmm.
it's happening. Might be the scale is different. It happens over, like in Arctic, it happens over a decadal scale. But in Hudson Bay, we see it in a very seasonal scale, in a very short span of time.
Okay. Okay.
So this was the research that we observed, and luckily it got published in GRL, and we are all happy.
Yeah. Okay. Yeah. That sounds really
Yep.
fascinating. Um, what I was interested to know more is like, what are some of the sort of, I know that there are several important findings from this study, but do you have any plans to take this one step further, or what is the plan beyond this paper?
The plan B has already been done, actually. The plan
Okay.
B was to further see that uh, how this is uh, affecting the stratification of the system. This,
Okay.
there has been no data on this in Hudson Bay. As I told you before, it's a very
Hmm.
data poor region. So we used it. Now, this time it was based on more on field data rather than on satellite data. But our understanding was the because there is an increase of river water in the system, and from the previous, like from the GRL paper, we also understood there is a decrease in sea ice melt also in the
Hmm.
system. So these two processes are changing in the salinity of the system.
Right.
So because of the changing in the salinity of the system, there might be a change in the stratification of the system, like how the water is getting layered,
Okay.
where it's happening. And the key objective of the basis project that I am or in this and in this system. So the key objective of this basis project is to understand what is the fate of the river water and whether river water or sea ice melt is dominating the control of physical processes in Hudson Bay.
Okay.
So
Okay.
using salinity and oxygen isotope data, what we observed is that, of course, we did observe that downwelling phenomena happening in the coast during the fall and in the summer because of the anticyclonic winds, water moving from the coast to the offshore. These were all there.
Hmm.
But very
Hmm.
surprisingly, we saw this river water is not only confined to the coastal belts, it is
Okay.
controlling stratification even in the northern Hudson Bay and in the offshore regions,
Okay.
where traditionally we thought that sea ice melt should dominate the whole process.
Okay.
But it
Okay.
is
Okay.
not. It
Hmm.
is the river water that is dominating the whole process rather than sea ice melt.
Okay. Okay.
So
Okay.
this caught us with surprise, and we are planning to submit this paper in a peer-reviewed journal.
Okay.
And yeah, so this was a very important finding that river water is controlling the whole, the salinity gradient of the whole water column is
Yeah.
absolutely being controlled by river water. Sea ice melt does control it, but very regional and specific the region. So nothing like a very big thing, which should have been considering the whole sea ice dominated system. So now, what are the implications of these things? The major
Hmm.
implication is that if there is so much of river water that is coming in Hudson Bay, because we know Arctic amplification is increasing the precipitation over the lands. If there is increased precipitation over the lands, we know that river water is automatically going to increase into the ocean, flowing into the ocean.
Hmm.
So this is number one. Number two is that now if we there are several rivers in Hudson Bay which are very regulated for hydropower generation, because we know
Hmm.
that in cold countries we do require hydropower
Yeah.
for the heat generation during the cold months.
Hmm.
So what is happening for that? So during the colder months, so during the fall, like September, October, November, December, so this time there is gushing of river water coming into the system, which shouldn't have been there in natural flow. Naturally, it should have been there in the spring, then decrease. But due to anthropogenic interventions, what we are
Hmm.
seeing is that there is huge amount of fresh water, specifically from the river system in James Bay. We are seeing
Hmm.
huge amount of fresh water coming into the system. Now,
Okay.
this fresh water is coming right into the winter time. Now, winter time, we know that sea ice forms. As we all
Hmm.
know that when sea ice forms, we have this brine released. There's a brine rejection.
Yeah.
Now, because brine is heavy, it sinks to the bottom. That enhances the deep water formation.
Okay. 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 Okay.
So now we are seeing a situation. We might see a situation where we have so much of river water coming in naturally and also coming in at a very late part of the season due to hydro regulation.
Okay.
So there is so much of fresh water. So which might also see that there might be reduced formation of sea ice and the mixing might very much impede. So because as I told you before, because if there is no mixing in the system, primary production, which depends on the nutrients from the bottom layer, travel up to the sea surface, it's not going to come. So it will be a very
Hmm.
low productive region, which will hamper the
Right.
whole food web system,
Food
and
web
it will
system. Yeah.
hamper like the coastal livelihoods, which depends
Hmm.
on this marine ecosystem.
Right,
So it's a
right,
very
right, right.
important thing that we're seeing.
Yeah.
We're going into a phase where river water can cause a problem for the coastal livelihoods in
Mm-hmm.
this
Yeah,
polar marine
yeah,
regions.
that's yeah, fascinating. Like, thank you for like going into those connections, because sometimes it might seem that okay, what is the point of science? But that it is, these are the observations which are very also very important for communities, the people, the biology. So yeah, so it is surprising how like
Yeah, yeah,
everything is like
yes.
linked to the system. And as you mentioned, the impact of anthropogenic activities, like it is very difficult for like to understand for the what could be the impact. But as you were saying, that the whole system is being disturbed by these activities, right? So yeah, so those are like very, thank you for like going into that domain,
Yeah,
and so that it's easier for people to link what is the point of this study, right? Yeah.
and yes. And also, I forgot to mention one more aspect of it. It also links to the acidification, like to the ecosystem stuff, is that the more of the mix, you do not have this mixing impeded, the more of your surface water is getting exposed to the atmospheric carbon dioxide. So more acidified waters you're forming on the surface. And this
Okay.
water is going directly into the North Atlantic Ocean via Hudson Strait into the Labradors. So you
Mhm.
have more amount of acidified waters into the North Atlantic Ocean. So that's also
Okay.
disrupting the whole system. It's changing everything. It's going to
Yeah.
change the food
Right.
web structure. But at the
Mm-hmm.
basis of all, it is the coastal livelihoods that is going to suffer for this
Yeah.
system.
Right, absolutely. Yeah. Okay. So, Dada, we're like going to transition a bit more into sort of more
Yeah.
the person behind the science. So that is you. So if you just want to sort of, so first of all, this is one question I've
Uh,
been doing. So I know we are both from the tropics, and we are studying sort of polar marine systems.
uh-huh.
So just the my first question would be like, how do you process that? Or I know you already talked about the process, how you started the program, but how do you feel about that? And the second question is like, okay, first, if you want to answer this question, then we can move to the second one.
Uh, it is a thrill of knowing. That's the most inquisitive thing that I can say is a thrill of knowing what's happening in that system, in that part of the system. I tried to know in the tropical regions, like in the lower part of the Bengal Delta, I think where you have also worked in. So, uh, but then I got this opportunity to work in Canada. I was trying to see that, okay, if there is river water, there is also sea ice melt there. There's another component to the system, how they are both interacting. So, science is always like what I say, koi, your topic or your
Mm-hmm.
title of the
Mm-hmm.
podcast channel. Your so it's like where, when, why,
Mm-hmm.
to know more and
Right.
more and more. That just fascinated me. And like
Mhm.
poles
That's,
are like another fascinating regions. It's like barren, more
mhm.
hardships, more. That adrenaline drive actually got me into more polar studies, to be very
Mhm.
frank and say. So yeah,
Right.
I'm enjoying doing polar studies, and I like to continue this for
Yeah.
my career, at least for some while.
Right, absolutely. So like a lot of the of our audience are sort of enthusiastic scientist. So basically, we have a lot of listeners who are sort
Yeah.
of considering like a career in the sciences. So as someone who has gone through quite a bit in the in your career, so I was going to ask you like, do you have any advice for enthusiasts or anyone who wants to study sort of like maybe similar pathway as you do? Do you have any advice for them?
Manjeet, for using the word enthusiast, science enthusiast, to pursue science in any field, irrespective of environmental science or like physical sciences, chemistry, biology, mathematics, we need to be an enthusiast. We need to be curious. We need to accept failures. So this is what I learned from my whole PhD thing is that we need to learn how to accept failures, how to accept frustrations, how to get things going. It will happen at one point of time,
Mm.
but we have to wait for it, give time to it, and keep believing on ourselves that what I am saying or what I am thinking, it's right. Be right
Mhm.
at the end. But we should
Mhm.
have the belief in ourselves that whatever I'm saying, it's right, and I will go forward with it.
Mhm.
Like PhD in the States or Canada can take over 5 years.
Yeah.
And likewise, if we compare with any other profession which just starts after masters, it just gives more money, where PhD
Yeah.
doesn't give that much money to it.
Yeah. Yeah.
So we should accept that. Please accept it
Mhm.
beforehand coming into PhDs or doing research. You are not going to be paid that much as your friends or colleagues are getting after engineering, getting a job,
Yeah.
and that. Please accept it. But the main
Mhm.
going is your science. You believe in your science
Mhm.
and you have to do for the science. That's
Mhm.
my first kind of advice. Be patient. It will happen. One day it will
Mhm.
happen. And for
Mhm.
polar science, of course, keep your like physical fitness is most important thing. So
Mhm.
if you want to go to the field and do stuff, so be physically fit,
Mhm.
mentally aware, and just do your science, enjoy your science.
Yeah.
That's what I'm going to say.
Yeah. Exactly. So yeah, it's great that you sort of mentioned the point about expectations, right? So it's sometimes we sort of I think it's important, especially when you're starting a PhD program, to know what you're getting into. So sometimes it's often like we don't really sort of understand what it doesn't mean that you have to go into a PhD with having this great idea. It's not that, but it's
No,
important to sort of
no,
like have that mindset that this is going to be difficult, but I'm going to get through this, right? And I think a part of
yes,
it is definitely the hardship that you talked about and the patience. I think that's what sort of gets you through it, right? Because definitely, as you said, that always there is like hope at the end, like light at the end of the tunnel, right? So as sort of night thickens, it
yeah,
gets darker, but there is definitely light. So I think it's important for all PhDs to sort of keep reminding themselves that, because sometimes it's very difficult. Sometimes there are various external factors. There are sometimes we are moving out of our comfort zone. We're living in another country. So there's a lot of different aspect that sort of goes into it. But like accepting that hardship because that's how sort of you and you're also like you're sort of like increasing your potential also. So yeah, any thoughts on that, Dada? Yeah.
yes. The one thing that I'm going to say at the end of the day, when you're doing a PhD or any research, I'm not saying particular to the PhD or something, it's yours. It's
Mhm.
something that you have created. You have been helped by others. It's yours. You own it. So at the end of the day, there is at least for me, I know it's a kind of a satisfaction that, okay, I know I've been working for this corporate firm and I know I'm getting paid more, but that's not my own thing. That's I'm giving it to someone else's name on it, someone else. But when you're doing a research, particularly in academic field, it's your work, your job,
Mhm.
your thing. So yeah, it does come with a lot of pain and stuff, but at the end of the day, it's your baby
Yeah.
kind of stuff. So you will learn to love it more and more day by day. So yeah, so that's what I want
Right.
to say.
Yeah. Right. Thank you so much, Dada, for ending it in a positive note. I think definitely like we see through source we also like sort of follow the path of our mentors and yeah, seeing your paper in GRL now, I'm very happy.
Yeah.
Congratulations again for that, and hope for your continued success.
Thank you, Mona.
Thank you. Yeah.